Last semester, we said that you could think of potential energy as a type of energy that is associated with the positions of particles in that system. If I have particles that are all at certain locations, I could associate a certain amount of potential energy given that specific configuration of particles in my system. If then I move some of the particles around to new positions, the configuration of the particles in that system would have changed, and I could assign a new amount of potential energy to that system. And therefore, I could meaningfully talk about the change in potential energy between the initial configuration of those particles and the new configuration of those particles. When we talk about electric potential energy, we will be concerned with the positions of charged particles in a system. So here is a system containing some number of charged particles. Some of these particles are positive charges, others are negative charges, and the particles themselves do not all have to have the same amount of charge. Whenever we calculate the change in potential energy between the initial configuration of a system and the final configuration of a system, we will use this equation. You might notice that one of the particles I drew in this picture is green. Now, let us say this is our initial configuration of particles in our system. But let us then move the green particle to a new position. So I could say right now, based on this system of charged particles, there will be some amount of potential energy associated with the system of particles. But then when I move the particle to its new position, there will be a different amount of potential energy associated with this new configuration of particles. The change in potential energy is going to be described by this equation. Notice that I only moved one particle. Q here is the charge of the particle that moves, and I am only allowed to move one particle at a time. What about the other term in this equation, the delta V? V initial and V final are the electric potential due to all the particles in my system that do not move, and V initial and V final are evaluated at the initial and final location of the particle that does move. So the way I'm going to think about this is the particle that moved initially was up here but is now down there. These 11 other particles that are stationary are all charged particles, so they all will contribute some amount to the electric potential at these two locations. The electric potential due to these 11 particles that do not move will have some value at the initial position. So I will say there is some amount V initial right here. And these 11 stationary particles will contribute some amount to the electric potential at the final position of this particle. So I will have some value for V final right there. I account for the charge of the particle that moves when I plug in a number Q here. I account for all the charges in my system that do not move in the calculation of delta V. Now you might be wondering, what if we move more than one particle? What if we want to move a whole lot of particles in my system? The way I would address that problem is we would say we'll begin with the initial state of our system, the initial arrangement of all the particles. We move one particle into its final position and we calculate the change in electric potential energy, and we'll write that number down. Then we move the second particle into its final position, and we could calculate the change in electric potential energy as a result of moving that second particle in its final position. And then we could move the third particle into its final position and calculate the corresponding change in electric potential energy from moving that third particle into its final position, and so on until we move all the particles from their initial position into their final position. Then we add up all the changes in electric potential energy and we find the total change in electric potential energy. In a future example problems, we will demonstrate a problem like that. In the first example problem, we are told that we have 2-point particles. The 2-point particles have electric charge of +2 and +3 coulombs. We're told that initially the two charges are separated a distance 1 meter apart, But then the plus 3 coulomb charge moves to a final position of 3 meters away, and we're asked to find the change in potential energy of the system. We said that whenever we work with this equation, we need to pay attention to which charge is moving. At any given moment, we are only allowed to move one charge at a time. In this equation, Q is the charge of the particle that moves. When I move a charge, it will have an initial position and a final position. Charged particles create electric potential. They're responsible for electric potential existing. There will be a value of the electric potential at every location in space. The delta V in this term is V final minus V initial. And V final and V initial are created by every charge in the problem that is not moving. One way you could think about that is the charge that moves cannot see its own electric potential. I am interested in what is the value of the electric potential at the final location of the charge that moves due to all the other charges that are present, and what is the value of the electric potential at the initial location of the charge that moves due to all the other charges that are present. In this particular example, I only have one charge that is not moving, the plus 2 charge. So to determine the change in potential energy of the system, I could write delta PE is equal to, now the charge that moves is the plus 3 coulomb point charge, so Q here will be 3. And the electric potential is set up by all the charges in the problem that are not moving. In this particular example, we only have one charge that is not moving. So the electric potential will be set up by the plus 2 charge. So I will write this for the moment as V final minus V initial. You might notice that I am using different color markers. I am choosing to draw the charge that moves in green, and I am choosing to draw the charge that does not move in purple. This just helps as a quick visual reminder of which charge is moving, which charge is not moving, so I don't accidentally plug the wrong value for electric charge in my equations. Now, as I said, V final and V initial are evaluated at the initial and final location of the charge that moves, but V final and V initial are created or due to the charges that are not moving. So V final will be the value of the electric potential 3 meters away from the plus 2 charge. V initial will be the value of the electric potential 1 meter away from the plus 2 charge. The plus 2 charge is not moving. So the equation for the electric potential due to a point charge is V equals KQ over R. K is Coulomb's constant, so I would write 9 times 10 to the 9. The charge that creates the electric potential is the plus 2 charge in this problem, so I will have 2. The final position that we are evaluating at is 3 meters away, so 2 divided by 3. And then minus V initial. K, Coulomb's constant, 9 times 10 to the 9. The charge of the particle not moving is still 2 coulombs. And the initial position we are evaluating the potential at is 1 meter away from the charge that is not moving. And then I will multiply this change in electric potential by the charge of the particle that is moving, 3 coulombs, and this gives me the change in potential energy. So now we have a number everywhere on the right-hand side of the equal sign, so we could plug this through a calculator and see what we get. So here we would have 3 divided by 3 gives me 1, then this will be 18 times 10 to the 9 minus 3 times 2 times 9 gives me 54 times 10 to the 9. And then when I send this through a calculator again, I get negative 36 times 10 to the 9. And this is the change in potential energy of the system of particles. Because this is a potential energy, this number will be in joules. Let us now ask, does this number make sense? Well, let's think about how we might visualize this system of particles actually evolving in the real world. I could imagine that there are two positive charges. I have a +2 charge initially placed down, then I just place a +3 charge down. As soon as I let go of that +3 charge, positive charge, I know the +3 charge will be pushed away by the Coulomb force. It will accelerate away. The +3 charge will gain kinetic energy as it moves away. If the +3 charge is gaining kinetic energy, I expect there to be a corresponding loss in potential energy. And indeed, what we found was the change in potential energy was negative, so that's okay. Also, as another note, this is a really big number, times 10 to the 9 joules, but remember that 1 coulomb of charge is a huge amount of charge. The actual numerical values of the charges we considered in this problem are not realistic. Usually charges would be on the order of microcoulombs or nanocoulombs. But just to make writing out this scenario easy, we chose to choose numbers like +2 and +3. Now let's consider what this scenario might look like if the charge were -3 instead of +3. Here we have the exact same scenario that we just considered, but instead of a +3 Coulomb point charge moving away from the +2 charge, we're considering a -3 Coulomb charge that's moving away. Because I changed the charge of the particle that's moving, I changed the color representing the -3 charge to red. In order to determine the change in potential energy of the system, we will again use this equation, delta PE equals Q delta V. The role of Q and delta V in this equation is going to be the same. Q is still going to be the charge of the particle that moves, and V initial and V final will still be the electric potential created by every charge in the problem that is not moving. And we are asking, what is the electric potential due to the charges that are not moving at the initial location and the final location of the particle that is moving? So here, when I plug in a number for Q in this equation, I need to include the sign of the charge. So in this case, Q will be -3. And because I did not change anything about the sign or magnitude of this charge or the initial and final distance away, I'm still going to get the exact same thing for V final minus V initial. I'll still have Coulomb's constant, 9 times 10 to the 9, times the charge of the particle that is not moving, which is +2, divided by the final distance away, which is 3, minus 9 times 10 to the 9 times 2 divided by 1. When I plug these numbers through a calculator, I find that the change in potential energy of this system is going to be positive 36 times 10 to the 9 joules. So this is our result. Let's ask ourselves, is this result reasonable? Is this how we expect the world to work? Well, let's first ask, is this scenario reasonable? Is it reasonable to expect there to be a -3 Coulomb point charge close to a positive point charge, and then sometime later this -3 charge is going to be further away? At first guess we might say no. We would say if we placed a -3 Coulomb point charge down and let go, we expect the -3 charge to be attracted towards the +2 charge. And the Coulomb force is the only force that is allowed to be acting on the charges. We're not allowed to be holding a charge or anything like this. So is there any possible scenario where you could have this be the initial picture, this be the final picture, and have the Coulomb force be the only force acting on these charges? One way we could realize this is to imagine that we place this -3 charge down and then we throw it before we let go. If I give this -3 charge an initial velocity to the right, the -3 charge will initially be moving away from the +2 charge. Now the +2 charge is going to pull back on the -3 charge, causing it to slow down. Eventually, this -3 charge will come to a stop and begin accelerating towards the +2 charge. But in this case, as the -3 charge moves away, it will lose speed. It will lose kinetic energy. If that -3 charge is losing kinetic energy, it will gain potential energy, implying a positive change in potential energy, which is what we found here.